Welcome to lecture 11, phase diagram part 3, engineering metallurgy. Today, in the last class, we have studied the type 1 phase diagram, how to determine the chemical composition of each phase and also the relative amount of phases. That means how much solid is present in a certain temperature, and then that solid, how much part A or how much part B is present. And today we are going to study type 3 phase diagram. In the case of type 3, it has like the basic characteristic of the type 2 diagram. Type 2 diagram is the metals completely soluble in the liquid state and completely insoluble in the solid state. The first one was metals completely soluble in the liquid state and completely soluble in the solid state. But in this case, in the solid state, metal will not be completely soluble. So before we go to the type 2 diagram construction, how to construct it, we need to understand the rule that is Raoult's law, which states that the freezing point of a pure substance will be lowered by the addition of a second substance, provided the later spelling was there's a typo. The latter is soluble in the pure substance when liquid and insoluble when solidified. That means if you have a combination of metals, that means a alloy system that contains two different metals, in that case the freezing point of the pure substance will be lowered by the addition of second substance. That means if we have substance A and substance B, if we add substance B on substance A, then the freezing point, let's say freezing point of A is 300 degrees Celsius and freezing point of B is 400 degrees Celsius. In that case, when we add metal B on metal A, then the freezing point of A will decrease. Okay, it will decrease. That's what it says, but there are some conditions. The conditions are that is provided that the latter is soluble in the pure substance. That means B must be soluble in A. Otherwise, this formula will not work. Okay, that means pure substance B must be soluble in A when liquid. Condition, if you go to the complete condition, that is when in the liquid state, so metal B must be soluble in metal A. Okay, and insoluble when solidified. That means when A and B are mixed together and then solidified, then metal B will be insoluble in metal A. This is the condition. Okay, under this condition, when metal B is added to metal A, then the melting point temperature of or freezing point temperature of A will that will not be the freezing point temperature of A. It will be the mixture of A and B. The freezing point temperature will decrease. Okay, that's what the Raoult's law states. Did you understand that Raoult's law?
Condition to sir.
Okay, the condition is that firstly, in the liquid state, when A and B both are in the liquid state, B will be completely soluble in A. It will be a solution. Okay, and B will be completely soluble in A. And when after addition of B, when this system is solidified in the solid state, B will not be soluble in A anymore. That means B will be separate from A. That is the condition. If this condition is satisfied, then if we add B in A, then the freezing point temperature will decrease of the system. Okay, we'll see with the example in the later slides. Now, the amount of lowering of freezing point is proportional to the molecular weight of the solute. Okay, And that means the molecular weight of B, it is how much decrease in freezing point will occur. It depends on the molecular weight of the solid. That means molecular weight of the B. Okay. So this is the construction procedure for type 2 diagram. That means metals completely soluble in the liquid state and completely insoluble in the solid state. So in this case, what happens is that if we consider a 100% A, that means there are two elements, element A and element B. For A, when 100%, then the freezing point temperature will be constant because it is pure metal. For the pure metal, we know that the freezing point temperature is constant, and that will give us a cooling curve which will have a horizontal line. Okay, and this horizontal line indicates the temperature. At that temperature, the solidification will be completed, and then it will go to the room temperature. But when we add metal B in metal A, that means 80% A and 20% B, then the freezing point temperature is decreased. Initially, it was, for example, 400, then it has decreased to 380, let's say, just for assumption. So the freezing point is decreased. That is what the Raoult's law say, that the freezing point will decrease, but condition is that the metal B has to be completely soluble in the liquid state in A, and in the solid state it will not be soluble. So another important thing occurs in this case is that we have also seen it in the type 1 diagram, that when two metals are mixed together, then the solidification does not occur at a constant temperature. Then there will be a starting point of the solidification, and there will be an end point of the solidification. Okay, and in this case, 80% A and 20% B, the solidification starts at temperature T1 and the solidification completes at temperature TE. At this temperature, solidification is completed. But the thing is, in here, when solidification starts in here and then solidification, the temperature comes to temperature T2, there will be again a horizontal line. Okay, and that horizontal line, an eutectic reaction actually takes place. Because and that eutectic, because of that eutectic reaction, a different phase is produced in which the metal A and metal B will stay separately, and we'll look into that, how the microstructure evaluation occurs at temperature TE, that means at eutectic temperature, and we'll also see the reaction that happens. And also another thing is that when you add in metal B in metal A, the temperature starts to decrease. That means the start of solidification point starts to decrease at T1. When you add 40% B in A, then the temperature is decreased further, and it continues. Okay, and if we come to the right side of this plot, then we see that at 100% B, when the B is 100%, then it has a constant temperature line. That means it is pure metal B, and the melting point temperature is constant. And also, when metal A is added to metal B, that means 80% B and 20% A, again the temperature, melting point temperature, decreases. And from the both side it occurs. Okay, and from the both sides, when temperature starts to decrease, and these two curves actually meets at a point. Okay, at some composition, these two curves meet, and that point is called the eutectic point. Okay, and at this eutectic point, the eutectic reaction occurs, and metal A and metal B precipitates separately, and they don't stay into each other. Rather than they actually solidifies separately. Okay, and we look into the microstructure evaluation, then it will be more clear. And from this graph, I think you should be clear now that when metal A is added to metal B, the solidification temperature decreases. And when metal A is added to metal B, then solidification temperature decreases. And they meet at a point where this point is denoted as eutectic point. Okay, that's what so far you need to understand. And what will happen at eutectic point, and I will discuss that in the later slides. Okay, and why this is actually constant temperature solidification. Okay, I'll also discuss that. Okay, any question in here?
Sir, I have a question that B percentage বা B ইয়াতে previous ইয়াতে বলেছিলেন আপনি যে B এর মেল্টিং বা ফ্রিজিং টেম্পারেচারটা বেশি থাকবে এর থেকে, কিন্তু
No, it's not. That was an assumption. It's not like the freezing point temperature has to be higher or lower. Okay, it can be like freezing point temperature of B can be higher than A. Okay.
স্যার ইউটেকটিক পয়েন্টের রাইট সাইডে কি স্যার এ বি এর মধ্যে সলিউবল হবে?
No, the A will be soluble in B in the liquid state, and also B will be soluble in A in the liquid state. After the eutectic point, it will not be soluble anymore because it will produce the solid. Okay.
Yes, sir. Thank you, sir.
Because the basic of this type 2 diagram is that in the solid state they will be completely insoluble. Okay, any more question? All right, then and how to construct this diagram? The similar way to the type 1, it's like you have to use different compositions like 80-20, 60-40, or whatever composition you prefer. For different compositions, you need to have the start point of solidification and end point of solidification. Once you get this start point and end point of solidification, then you can construct the type 2 diagram. How to construct that? In the case of type 2 diagram, we know the composition is coordinate system is the temperature and let's say this is 100% B and this is 100% A. In this case, the temperature versus composition. And in the case of temperature versus composition, when the composition is 80% A, 20% B, that actually indicates this alloy, and then 60-40 indicates another alloy, like this. For different alloys, you need to have the initial temperature of solidification. Let's say this is initial temperature of solidification for 100% A, and then this, and then this, and this is the eutectic point here, and then this is the start point of solidification. Once you get all the start point of solidification, and end point of solidification will be constant for all the alloys. The end point of solidification will be fixed. Okay. The eutectic point is the end point of the solidification for type 2 diagram. So in this case, to draw the diagram, you have to just connect the lines to get the liquidus and solidus lines. So this will be the liquidus line, this will be liquidus line, and the horizontal line will be the solidus line. Below this horizontal line, there will be the materials will be completely solidified, and above this liquidus line, the metal will be completely in the liquid state and completely soluble. And in this case, in the two-phase region will be here, like solid and liquid phase. Solid phase and liquid phase will be here. In this case, in the solid in here, there will be B present in A. Okay, A will be soluble in A, and that is why the B will be present in here. Okay, this is the two-phase region, this is single-phase region, and this is single-phase region. This is the single-phase liquid, and this is the single-phase solid. Once you complete the, okay, any question?
End point solidification, the temperature সবার জন্য সেম হয় কেন স্যার?
Sorry, end point. We will look into that when we analyze the individual alloys. Then we will see that why this is occurring. Okay.
লিকুইড সলিড ইন্টারফেস এখানে কি স্যার সলিউবল হবে?
Yes, there B will be soluble in A and A will be soluble in B. Okay.
Yes, sir.
Okay, we will see that. Okay, then it will be more clear. So once the diagram is complete, we can actually show the diagram like this. Like this, the completely liquid solution above the solid S line, so liquid S line, and below the solid S line, there will be solid A and solid B will be present separately, and they are not completely soluble. Okay, they will be separated. Okay, and in this case, when sorry, I had a actually made a mistake in here. When the in the two-phase region, there will be liquid, and when the solid is formed, that will be the solid of A. And in this case, there will be the solid of B only. That means whenever the solid, because the basic is here is that completely insoluble in the solid state. That means in the solid state, A cannot stay in the matrix of B, or B cannot stay in the matrix of A. So there will be complete solid A, which will contain 100% A. Okay, and liquid will contain A and B, mixture of A and B. Okay, is it clear?
Yes, sir.
So আরেকবার বলে ভালো হয়েছে স্যার।
Okay, so according to the base rule of type 2 diagram, it says that metal is completely soluble in the liquid state, but completely insoluble in the solid state. That means whenever a solid is formed, that solid will not contain A and B both. Solid can only contain either A or B. Depends on the whichever the concentration is higher. Let's say if the concentration of A is higher from this point to that, then the only solid A will be produced in this region when the temperature decreases from that point. And in the liquid, there will be A and B, mixture of A and B. Okay.
Yes, sir.
All right. So now we would like to actually understand how the solidification occurs. Okay. And in the case of solidification, if we consider the eutectic point first, this is the L11. Okay. If you consider the eutectic point at which the solidification occurs at a constant temperature. That means at a certain composition between A and B, the solidification will occur at a constant temperature. Okay. And obviously in the solid, there will not be the mixture of solid A and solid B. That means if a crystal is formed, that crystal can only have either solid A or solid B. Okay, so at this it is true only in the case of all alloys, but the temperature that I was talking about, the eutectic temperature, at the eutectic composition, the eutectic temperature occurs. We remember that it will be necessary for all other investigations, like all other alloys if we want to investigate. So it means that whenever the composition of liquid is 60B40A, then the solidification will occur at a constant temperature, and that is the eutectic temperature. And the reaction that will take place in this eutectic point will we denote it as eutectic reaction. Okay, let's try to understand how solidification occurs in here. This is the eutectic temperature composition of an alloy. This alloy has a solidification a start of solidification temperature and end of solidification temperature are the same. Okay. So at temperature T0, it is completely liquid. Okay. And solid A and solid B is completely soluble in each other. And when the temperature reaches E, that means at eutectic point, then the solidification starts. Okay, in the case of when solidification occurs, actually metal A and metal B solidifies separately. And the eutectic reaction that I was talking about in the previous slide, that is the liquid, when the liquid is heated, then solid A and solid B forms. Sorry, when liquid is cooled down, then solid A and solid B precipitates separately. That means they solid A and B is not mixed with each other in any way. And that's what the eutectic reaction actually, and this reaction takes place at a constant temperature. That means the start of solidification and end of solidification for this reaction is constant. And this the condition of occurring this reaction is a certain composition of metal A and metal B. And that composition is called eutectic composition. Okay. And now when temperature reaches at the eutectic point, okay, then solid, let's say if the whichever solid has higher melting point temperature, as we have seen in the previous slide, is that metal A has a higher freezing point temperature than metal B. And this is the eutectic point in here. If you just make an schematic in here, that is the eutectic point, and this is the eutectic alloy, and it has a composition of 60B and 48. Okay. When the temperature reaches at eutectic temperature, the metal that has higher melting point temperature starts to solidify first. Whenever metal A starts to solidify, both sides of metal A, in the both side of metal A, metal B also starts to solidify. Okay, that means, and it propagates that way. That means metal A, a crystal starts to form like this. Metal A crystal, that crystal starts to propagate in this way, and also on the both side of metal A, metal B starts to precipitate. They actually solidify separately. Okay, and that's how the crystal structure evolution of crystal structure occurs. Okay, and that means in the step 1, it is completely liquid. When the temperature reaches the eutectic point, then solidification starts. Okay, and how the solidification starts? Metal A starts to precipitate, become a solid, and then on the side, both sides of metal A, metal B starts to solidify. When the metal B starts to solidify, on the other side, metal A again starts to solidify. Okay, that's how the crystal structure actually grows, and that is why if you look at the microstructure in the solid state, then you'll see microstructure like this, and this is called the eutectic mixture. Okay, this is called eutectic mixture. It's not a solution. Okay, that means in here the black lines and white lines are indicated by metal A or metal B. Okay, if you indicate the metal A as black lines, then the white lines will be metal B. That's how the crystals grow. Okay, okay, any question?
স্যার আমাদের এই টেস্টের প্র্যাকটিক্যাল অ্যাপ্লিকেশনটা কি?
Okay, in the case of practical application, is the mechanical property. Okay, when the metal A and metal B produces crystal structure like this, it will have a different mechanical property. Then if all the crystals, if there is also, like for example, sometimes it can occur, I'll show you that, sometimes it can occur like there is the crystal of metal A, there are so many crystals of metal A, and there is a mixture of eutectic mixture. In that case, the pure metal A, the crystals of pure metal A has a different mechanical property. Let's say the pure metal A has a elastic modulus of 200. Okay, and when the metal A and metal B are mixed together, that might have a modulus of elasticity, let's say 400. When these two crystals are combined together, then you will have a different elastic modulus, and that might be like 300. Okay, so a different mechanical property can be obtained.
Yes,
Did you
sir.
get the point?
Ji, sir.
Okay. Okay. Any other question in here at the eutectic point? What the reaction or the evolution of mechanical properties? Sorry, or the crystal structure. Okay. If not, then we'll propagate. Okay. Let's move to the alloy 2. What happens in the case of alloy 2 when we solidify it? And another thing I would like to mention in here is that whatever temperature it starts to solidify the alloy 1, whatever rate of cooling you apply, in this case, you will always get a eutectic mixture. Okay, the final solid will have like solid A and solid B separated. Okay, and you will get a uniform distribution of solid A and solid B in the microstructure. And now come to alloy 2. For alloy 2, at point 1, it will be completely liquid, and A and B are homogeneously distributed in the liquid. Okay, it's a homogeneous mixture. When the temperature reaches point 2, that means when the temperature reaches T1, then solid A starts to solidify, but there will be no solidification for solid B. Okay, that means at this point there will be crystals of solid A. That means the nucleation of solid A starts to occur and solid A starts to form. When the temperature decreases to temperature T2, then the amount of solid A starts to increase. Okay. When the temperature reaches T3, then the primary A starts to form. Okay, and that the crystals of A will be formed, and liquid 2 will have both A and B. Okay, and if we want to determine how much A is produced at temperature T2, sorry, at temperature T2, how much solid is produced, that means how much metal A has been solidified, then we have to apply the rule 2. That means the relative amount of each phases. And how do we apply the rule 2? We need to draw a tie line here. Okay, if we draw a tie line, the tie line actually intersects in the solidus line at temperature T2 at this point. And this point actually indicates the composition. First, if we want to get the composition, the solid will have a composition of 100% A. That gives us the 100% A composition. And in the liquidus line, this point indicates the chemical composition of liquid. So liquid will have a composition of 30B, 70A. That means liquid will have composition of 70A and 30B. Now, how much percentage of solid has been produced at the temperature T2? To find out that, we need to have the total length of tie line. The total length of tie line is 30. And to get the percentage, then we have to find out the amount of solid. And that will be, we have to find the length, this length, that means up to the liquidus line because of the lever rule. Okay. Up to this length will give us the how much percentage of solid A has been produced at temperature T2, and then this length will be like 30 minus 20, 30 minus 20, and that will give us the percentage of solid at temperature T2. Okay, and that's what I have shown in here, like the chemical composition of liquid is 70A 30B, and chemical composition of solid that has been produced, which is solid A, is 100%. And if we want to find the relative amount, then we have to find out using the the numerical values that I have shown you, or you can use this like at T2X2 and T2L2, which is shown in here. Like T2, this point is denoted as T2X2, this length, and X2L2. Okay, this length can be used to determine the percentage of solid and percentage of liquid. Okay, so so far, do you have any question in here? Okay, so when the temperature reaches at 4, that means when the temperature reaches eutectic temperature, TE. Now, first we need to determine what is the composition of liquid and composition of solid. At this point, if we draw a tie line, that tie line is actually this horizontal line, and that intersects at this point and intersects at this point. That indicates that at temperature at point 4, just before that means that just before the eutectic temperature. Okay, the chemical composition of solid is still 100% A, and chemical composition of liquid is how much? We can read the chemical composition of liquid from the liquidus line, right?
Yes, sir.
So in this case, the chemical composition of liquid will be 60B30A. Did you understand this?
Sir, abar ekটু বলে দিন।
Okay. So for at temperature T2, let me clear it. At temperature T2, if we want to find out the chemical composition of liquid, then we move to this point, right? We move to this point, and that point gives us the chemical composition of liquid. Okay, and at temperature TE, the chemical composition, if we want to find out the chemical composition of liquid, then we have to move to this point. Then what is the chemical composition of liquid?
Sir,
60A40B.
No, it actually indicates B. The values in here actually indicates the percentage of B. That means 60B, 40A. Am I right?
yes, sir.
Any confusion?
No, sir.
Okay. So when the temperature reaches the eutectic temperature, the liquid has a composition of 60B30A. And what is the significance of this? What is the significance of 30A 60B? This is a special composition, right? Sorry, 40A. 40A 60B. Isn't it a special composition?
Yes, sir.
It is the eutectic composition. Okay. And since it is an eutectic composition, so the solidification of this liquid will occur at a constant temperature. That means temperature will not drop anymore. At the constant temperature, solidification of this liquid will occur. So if we want to see the microstructure just before temperature TE, that means before starting the solidification, temperature has reached temperature TE, but solidification has not started yet, then the microstructure will be like, there will be grains, the crystals of solid A. Crystals of solid A, and the rest of will be the liquid at eutectic composition. And this liquid will solidify at a constant temperature, and the solidification process will be similar to the alloy 1. The alloy 1 has the solidification procedure in which the metal A starts to solidify, and then alongside the metal A, metal B starts to solidify. And like this way, grains are formed, like with metal A and metal B staying together, but they are not mixed. And this is called eutectic mixture. When this kind of grains are formed, where metal A and metal B stays separately, then that is called the eutectic mixture. So after the solidification is complete, the temperature is still at TE. After the solidification is complete, the temperature will be still at TE, but when the solidification is complete, the rest of the, if we look at the microstructure will have the pro-eutectoid solid A. That means the solid grains of A that has been already produced from temperature T1 to TE, that will remain same. They will be unchanged. But the rest of the liquid, once solidified, then they will have the eutectic mixture present. They will solidify as eutectic mixture. That means the rest of the grains will be the mixture of solid A and solid B. Okay. Any question?
Relative amount of solid কিভাবে বের করব স্যার?
In which case?
T2
See, at TE,
T or T2 যে কোনো একটা টেম্পারেচার।
in the case of T2, if you want to find out the relative amount of solid or liquid, right?
স্যার
Okay, so at temperature T2, if you want to find out the relative amount of space, then you have to draw the tie line, right? And what is the tie line here? Here tie line is a horizontal line, T2 to L2. That is the tie line. And the total length of tie line will stay at the bottom, right? That is T2 L2 is the total length. And if you want to find the percentage of solid, then you have to consider this length up to the liquidus line, from the alloy to the liquidus line. This length is x2 L2. Okay, and this will give you the percentage of solid. And what is the value of x2 L2? That is 30 minus 20. Okay, 30 minus 20. And what is the T2 L2? That is total length from here to here, from here to here. So that is 30. So we'll get the chemical composition from here, like 33.33% at temperature T2. Okay. Any question?
লিকুইডাস লাইন আমরা তো লিকুইডাস লাইন আছে লিকুইডের।
No, that's the thing. That's why you need to concentrate when I talk. Okay, because there were two rules. One rule says the chemical composition, and that is a straightforward rule. And another chemical composition, how do we find it? To find the chemical composition of liquid, we move to this point, and then we read the composition from here, and that will give us the chemical composition of liquid. And for the solid, we go to the solidus line and we get the chemical composition of solid. But in the case of when you want to find out the relative amount of solid or relative amount of liquid, in that case, you have to, the rule says that you have to maintain the rule that it is a lever rule. That means opposite. When you want to find the percentage of solid or percentage of liquid, then you have to apply the lever rule. That means if you want to find out the solid percentage, then you have to consider the liquidus line. And then if you want to find out the percentage of liquid, then you have to go to solidus line. Did you understand my answer? Hello? Did you understand? Okay. So and if you want to more clarification, then I can give you another example. Is that, let's say you have a line in here. Okay. At the start point, there will be very small amount of solid, right? When the solid at temperature T1, solid will be very small amount of solid. When the temperature decreases to T2, the amount of solid increases. When temperature decreases here, then amount of solid decreases here, amount of solid increases, right? So it is a common sense, right? If you just apply your common sense, then you can see that as the temperature decreases, the amount of solid will increase. Okay.
Yes, sir.
All right.
Yes, sir.
Okay, now this is the graphical illustration. Like when the temperature reaches at T4, that means just before solidification, then there will be primary A. That means the grains of A that is already developed. Okay, the grains of A will remain like this, and the liquid that is present in here that will have a composition of eutectic composition, and because of that eutectic composition and the temperature is also eutectic temperature, so the reaction will be now the eutectic reaction. The eutectic reaction says the liquid when cooled, solid A and solid B will be solidified separately. Okay, and the microstructure will look like this. That means after solidification, the rest of the liquid that solidifies, like solid A and solid B separately. Okay, so the question that Samira asked, like what is the significance of studying this kind of diagrams or the microstructure evaluation? Okay, so when we do the slow cooling, then what happens is that you can control. There will be certain volume fraction of eutectic mixture. So the final composition in this alloy will be like there will be let's see the composition just above the eutectic point. The chemical relative amount of space, that means the liquid percentage will be 33% and the solid percentage will be 67%. That means here 67% of crystal A and 33% of mixture of A and B is present. So the chemical composition will be, mechanical properties of this structure will be completely different. Okay, and if the percentage of this solid A can be controlled in here, like for example, if you go to the diagram here, if you just quickly solidify from here at temperature, when the temperature is at T2 and then you quickly cool it down, then the solid grain that has been formed will have like 67% liquid and 33% solid. So there will be 33% solid of A, and once it is cooled from this temperature very quickly, then the rest of it will be the mixture of A and B. Okay, so in this case the solid A is only 33%, and when we do the slow cooling, then solid A will be like 67%. So this one and the 67% solid A crystal that has 67% solid A and a crystal that has 33% solid A, is this going to show the same mechanical property? What do you think?
No, sir.
Different. So that's how you can control, get a wide range of mechanical properties by cooling an alloy from a certain temperature very quickly or very slowly. You can get different microstructure, and that will give you different mechanical properties. That's why we study the phase diagram. Okay. Okay, now another question that can be raised in here is that when the temperature is below this eutectic point temperature, like at this point, okay, that means when the temperature reaches this point, how much solid A will be there and how much eutectic mixture will be, solid B will be there. That might be the question. Then you have to draw the tie line here. You draw the tie line, and that will give you the same chemical composition like initially it was 20B80A. Okay, that means solid A and solid B are not mixed together in the solid state. Okay, they are separate, but there will be two phase present in here. One phase is solid A and another phase is eutectic mixture. Do you understand? There will be two phases, but the solid A and solid B is completely chemical. In terms of chemical composition, there is solid A and solid B stays separately, and the overall chemical composition is the chemical composition of the alloy. Okay, for the same chemical composition, you can have different mechanical properties. Okay.
Sir, eutectic mixture বলতে কি বোঝানো হয়েছে স্যার?
Eutectic mixture is the mixture of solid A and solid B, and they stay separately. That's what I have shown in here. Here, solid A and solid B separate stays separately. Okay, and this mixture is called the eutectic mixture. Understand? You need to respond. If you ask questions, then you need to respond. Otherwise, it is very difficult. At least say yes, sir, or no, sir. I want more clarification. Okay. You have to say that. Otherwise, you will not understand, and I will not understand whether you have understood or not. Okay, now for alloy 3, what will happen in the case of alloy 3? I think you can guess it now. When the temperature is at T2, solid B will start to solidify. And when the temperature decreases from this point, then the amount of solid B will increase, because the amount of solid B, how can we determine the amount of solid B? Amount of solid B will give us, from this length, we can find out the amount of solid B. As the temperature decreases, the amount of solid B increases. When the temperature reaches at this point, eutectic temperature, if we see, the percentage of solid can be found from this length, solid B can be found from this length, and the chemical composition again becomes the liquid that is remaining will have the chemical composition of eutectic mixture, sorry, eutectic composition, and the temperature is also at eutectic temperature. So the eutectic reaction will take place, and the solidification will occur simultaneously. That means solid A and solid B will solidify simultaneously. And in this case, what will be the microstructure? The grains that has been formed from temperature T3 to temperature eutectic temperature will remain as it is, and then rest of the liquid will be like eutectic mixture. That means in this case, this is solid B, and this is the eutectic mixture, and on the left side of the eutectic point, there will be the microstructure of the grains will be solid A, and this will be the eutectic mixture. Okay, any question? Okay, so now I told you that I'll discuss the why if we draw a cooling curve here, let's say at this point, at point 1 the temperature is here. Okay, at point 2 the temperature will decrease, and then here the solidification will start. Okay, and then that's why the curve, the slope of the curve will be changed like this. Okay, and when the temperature reaches at eutectic point temperature, the composition actually becomes eutectic composition. That is why the solidification at this point actually occurs at a constant temperature. Okay, that is why this horizontal line is present in here. Okay, did you understand why this horizontal line was in the in the first slide?
স্যার আবার একটু বললে ভালো।
If we move to the first, this one, okay, in this one, as you see that the solidification actually starts at T1 for 80-20, right? And when the solidification starts, the slope of the curve actually changes. Okay, the slope of the curve, the changed slope will continue up to T2 and at TE, and at temperature TE, solidification actually occurs at constant temperature. Okay, and that is why because at temperature TE, the composition of the liquid will be the eutectic composition, and because of that eutectic composition, eutectic reaction takes place, which is an isothermal reaction, and that is why the temperature remains constant at this point. Okay.
Yes, sir.
And what is the self-study? What will be the self-study? You have to submit an assignment in the next class. That means on Monday. The assignment will be about the solidification of alloy 3. How the solidification occurs in the case of alloy 3, how the microstructure evolution occurs. That means the microstructure or at temperature at 0.1, microstructure at 0.2, microstructure at 0.3, microstructure at 0.4, at 0.5. 4 is just above the just before solidification at temperature TE, and 5 is after solidification at temperature TE. And then the at room temperature, what will be the microstructure, and at the same time you have to show the chemical composition and relative amount of phases at temperature T3, T4, T5. Okay, that will be your assignment.
Chemical
Can you do it?
Relative amount
of these phases. Sorry,
আমাদের কি কি সাবমিট করতে হবে? কেমিক্যাল কম্পোজিশন আর রিলেটিভ অ্যামাউন্ট আর স্যার ফেজ ডায়াগ্রাম, মানে ওই ক্রিস্টাল স্ট্রাকচার।
yes, crystal structure, and also the description. Okay, like description would be for alloy 2. Let's say description would be like at 0.1 the metal A and metal B is completely soluble, and there will be uniform distribution of A and B. Okay, and if you want to see the microstructure, then microstructure, you can draw the microstructure like this. It is a schematic microstructure. Okay, like draw a box and then show the uniform distribution of A and B. It is a liquid. Okay, and when the temperature at T1, then the solidification starts. Since the solidification starts, there will be some grains of metal A in this case, and when the temperature reaches at T2, then the amount of grain will increase, and also the size of the crystal will also increase. Okay, and then you can show in here the chemical composition. If you want to show the chemical composition, then chemical composition will be 80-20. Okay, in this case chemical composition will be 80-20, and in this case chemical composition will be very close, so it will be very small amount of solid. So the chemical composition is the solid chemical composition is 80A, sorry, not 80, 100%, 100% A, and liquid composition will be, we can read it from very close to the to this, so it will be like let's say 21, for example, 21B. The liquid composition will be 21B, and when the temperature at T2, the solid composition is still 100%, and the liquid composition will be like 30B. 30B will be the liquid composition. Okay, and then temperature when decreases up to 4, then again the amount of solid increases. Okay, amount of solid increases like this, and the solid will have a composition of 100% A again, but liquid will have a composition of 60B, 40A, that means 60B. And for each cases, you can find the relative amount of each phases, like how much percentage. In this case, it is not possible. It is 100% liquid, right? In this case, only single phase and 100% liquid. And in this case, since you have considered the 21B, then you can find a small amount of solid. So you can find the solid percentage and liquid percentage. In this case, you can find the solid percentage and liquid percentage. In this case, you can also find the solid percentage and liquid percentage. And when the solidification occurs, then the microstructure would be like the solid particles, the solids of A will be present there, and rest of it will be the eutectic mixture. Okay, at room temperature after solidification. That means at 0.5 or below, it will be the same. And also you can find the relative amount of phases will be same as 0.4. The relative amount of phases present at 4 will be same as relative amount of phases present at 5. Okay, and also at room temperature, it will be the same. Okay, that's how you describe, and also you draw the microstructures, and you explain, you find out the chemical composition, and you find out the relative amount of each phases for alloy 3. And you should be honest, and you should not look at the book, because this is given in book. Okay,
Sir,
try to do it yourself. Okay, without looking at the book, try to do it yourself. Okay, then you will understand. And if you don't understand, then you can ask me, or you can take help from the book. Be honest to yourself. Okay.
Yes, sir.
Yes, sir.
Because if you don't become honest, you just copy and paste from the book, then you will not learn. And you are, I think you guys are in third year, and you should be really responsible. Okay, to learn, you should learn. Okay, you just don't try to copy, or don't try to do anything else. And the instruction for this assignment is that you have to upload the assignment in the website. That means that is called the Google Classroom. You have to upload it in the Google Classroom. Okay, and I will create an assignment, and you have to upload it within 9 o'clock on Monday. All right.
Okay, sir.
And now I'm missing, I have missed one thing, is that there is a denotation for the alloys. For binary system alloy, this is 100% A and this is 100% B. This point actually separates the name of the alloys. Like before the eutectic point, eutectic composition, the alloys are called hypo-eutectic alloy, and after the eutectic mixture composition, it is called hyper-eutectic alloy. Hypo is before eutectic and hyper is after eutectic. Okay. So now, any question? We're going to finish type 2.
T2 temperature 100% solid, 30% B, 60% B. It is solid.
30% B and
60% B, 21% B. Solid na liquid.
I don't understand your question. Can anyone clarify his question?
30% B 60% E হচ্ছে স্যার ওই সব ক্ষেত্রে তো স্যার 100% সলিড থাকছে
Yes, solid will be 100% because
36
the solid percentage is given by this line, and solidus line actually starts from here. Okay, here up to here and here. This is the whole thing is the solidus line, and you should always remember that solidus line and liquidus line should intersect at a point, and that is this point. At this point it intersects. Okay,
কোশ্চেন 30% B 60% B এটা লিকুইড সলিড
এই নিচের গুলা
30% B যে করলাম স্যার আমরা T2 টেম্পারেচারে তো এটা কি স্যার লিকুইড না সলিড ধরলাম যে
what do you think?
লিকুইড হওয়ার কথা স্যার
Yes, of course it is liquid. Why not? Because at temperature T2, this tie line indicates that tie line intersects in the liquidus line at L2. Okay, and this point will give the composition of liquid, right?
Yes, sir.
So this 30% B is the composition of liquid, isn't it?
Yes, sir.
Did you understand now?
Yes, sir.
Okay. Okay, any more question? This is an example of aluminum and silicon alloy system. In this case, this is a type 2 phase diagram. It can be created using aluminum and silicon. Silicon has a melting point temperature of 2600, whereas aluminum has melting point temperature of around 640 or 650. Okay, 650. And when silicon is added to aluminum, the melting point temperature decreases, and there is a eutectic formed at like 12%, 11%. 11% is it going to be, or 12%? Let's say 12% silicon. When 12% silicon is added to aluminum, then an eutectic point is formed in here. Okay, and the solidification liquidus line is indicated by this and that, and solidus line is indicated by this, here and here. Okay, so in this case, if we look at the pure aluminum, it will have an uniform crystal structure with all the aluminum grains. And when the 2.8% silicon is added to the aluminum, that will be like here is 10%, like 2.8% will be somewhere like here, and there will be some grains of aluminum. Okay, so these white regions actually indicate the aluminum grain, and the rest of it, when the temperature reaches to the eutectic temperature, then composition becomes eutectic composition. Eutectic composition, and that eutectic, because of that, there will be some mixtures of aluminum and silicon. Okay, that is the eutectic mixture. This is the eutectic mixture. When the silicon percentage increases like 12% at the eutectic mixture, at eutectic point, at this point, then it will be the uniform mixture of aluminum and silicon. The whole microstructure will look like this. That means it is a mixture of aluminum and silicon. And when you increase the silicon content, then you will start to find the silicon grains with eutectic mixture. That means when you move from this point to that point in this direction, then at first there is 100% aluminum. Then when you add silicon, then you will find the aluminum silicon mixture. You add more silicon, you will get the 100% eutectic mixture. And then you add more silicon, then you will start to find the silicon grains with eutectic mixture. And then you add more silicon, like 50% silicon, then you get more grains of silicon and the mixture of aluminum and silicon. And if you solidify the pure silicon, then there will be 100% silicon grains. Okay, that's how this diagram works. Okay. Any question here?
স্যার ইউটেকটিক টেম্পারেচারটা 60 বি আর 48 তে ইউজুয়ালি কি হওয়ার কথা নাকি ডিফারেন্ট টাইমে ডিফারেন্ট?
No, it depends on the elements. Okay. For example, in here, like for aluminum and silicon, it is 12%. Okay. And if you use a different system, alloy system, for example, aluminum with carbon, then it might be a different point, different composition. Okay.
Sir.
The first one that we have discussed in here, it is actually a hypothetical diagram. Okay.
Yes, sir.
It is not concrete. That eutectic composition can be any composition. And also the melting point temperature of A, B can be different. This is the perfect example, right?
Yes, sir.
Here aluminum melting point temperature is less and silicon is high. Okay, so I think we cannot continue for type 3 diagram. It is very complex, and I would recommend you to study the previous 2 lectures again more clearly to understand type 3 diagram. Okay, so in the next class, we'll discuss about type 3 diagram.